Okay, hey guys. It's Organic Chemistry 2 review by Jessica. You guys all here for Orgo 2? Yeah? Good. Okay. This session is being streamed on YouTube, so if you guys want to re-watch it later, it's on YouTube. It's on the SARC YouTube page. Hello. Are you here for Organic Chemistry 2? Nope? Okay.
Do you know what this section is for C and D though?
This is C and D, but this is Orgo 2.
Are there multiple?
Is that the right time?
Yeah. Never mind, I forgot.
Okay. Hello. Are you here for Orgo 2? No? Yeah, okay. Okay, so yeah, this is being streamed on YouTube. And oh, if you guys have any questions, feel free to ask. I may tell you to hold them to the end if I feel like they're going to take too long and I won't have time to go over them. But feel free to ask questions, and if I have time, I'll answer them right away. Okay, so let's get started. I have it separated for different sections from the ACS official study guide. I recommend that you guys study from this. If you don't have it, get it, definitely. When I took the ACS, it was the most similar thing to the exam ever. So these questions are straight from the official study guide. The first section is the structure. Well, the first section is nomenclature, but we're not doing that today because I couldn't do all of them, and I felt like you guys know nomenclature. So this one is structure, hybridization, and residence. So what are the respective hybridizations of the atoms numbered 1 to 4 in this compound? Do you guys remember how to do this all? Yeah, so this first one has 1, 2, 3, 4 substituents, 4 electronic groups, right? So it's a tetrahedral. So it's going to be an sp3, right? So already we can cross out the first 2 because they start with 2 sp2s. So then we go to the second one. It's got 1, 2, 3 groups on this carbon, right? So that's going to be an sp2, right? Those are both sp2s, so we have to move on. This carbon, right, it has 2 H's, and then it also has these other 2 substituents, so it's also a tetrahedral. So that's also going to be an sp3. And this one's an sp2, so we can cross that one out, and we pretty much have our answer. And just for clarification, this last one is on a triple bond, right, which is always an sp. So the answer is D. Any questions on that one? Okay, good. Okay, so which structures would be classified as aromatic, right? So this is Orgo 2. You guys did this semester. Do you guys remember 4N plus 2? No? Huckel's rule, right? Yeah. Do you want me to go over it really quick? Yeah? Okay. So Huckel's rule, right? N has to be integer. So it can be 0 to infinity as long as it's not any kind of decimal point, right? And then whatever, if you can get a number with an integer, then it's aromatic. I know that kind of doesn't make sense. But say if your integer is 1, right, then you would get 6. Having 6 pi electrons is aromatic, right? So if you put 2 in there, hi. 8 plus 2, 10 is also aromatic. 3, that's 12 plus 2, 14 is also aromatic, right? So if we go and we count these, this one has 1, 2, 3, 4, 5, 6, right? So it follows in Huckel's rule. It has the right amount of electrons. And then it also has to be completely resonance, right? And this has that because we can move it around completely within the ring. Do we see that? So that one's aromatic, so we check that one off. We move on to number 2. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? If my N is 3, I get 14, right? So that's not going to give me a fraction. That works. That's also aromatic, right? And you see that this can be completely resonance throughout all 3 of these rings. Okay, so that one's aromatic. And then we move on to this one. These are cations, right? So we're not going to count them as electrons. So we just have 1, 2, 3, 4, 5, 6. I can move this over. I can move my cation over. I can move this bond over. So this is also completely resonance, right? It's because resonance throughout the entire ring. and it has 6, which also follows Huckel's rule. So that's why the answer is A, right? Because they all follow Huckel's rule, and they all have complete resonance throughout the ring. They're all rings. They're all planar. They have to be planar as well. Any questions on this? Okay, perfect. So now we're moving on to acids and bases. It's the next section. So which structure helps explain why an anilium ion is a stronger acid than an ammonium ion? So I know acids and bases was a long time ago, but when you're an acid, are you donating a proton or are you gaining a proton? You're donating protons, right? Getting rid of protons. And you want to be stable after that. If you're more stable after you get rid of a proton, you're more likely to get rid of a proton, right? So it's asking, why is this one more stable than this one after it gives rid of a proton? So why is this one a stronger acid? So pretty much it's just asking for a resonance structure. That's all. So if we get rid of a proton, we'll have H2, right? So it's going to look something like this. And these will have little double bonds. Right? And then if I were to draw a resonance structure of this, this could come down and make a double bond. And then this pi bond could come right over here. Now that my N has 4 bonds, right? It has 2 hydrogens and the double bonds. That's going to be positive. And then this pi bond is going to make a negative charge. And that negative, that anion can go all the way through the ring, right? But out of all of these, the only one that matches is B. That's the only true resonance structure. Hello. Any questions on this one? It's B. Does it make sense that that's the only resonance structure for that guy? Why what? Why the NH4? So it's asking why is the other one with the benzene ring, right? Why is that one more acidic? And the reason it's more acidic is because it has resonance structures. So it's just asking, which one of these resonance structures helps to explain that. So it's really just asking which one of these is a true resonance structure because the other 3 aren't correct. They have the wrong amount of charges, or they actually all have the wrong amount of charges. Yeah, the stronger acid is the one that's more stable after it releases a proton. And we know that having resonance increases stability, right? So it's going to make more sense that the other one is more stable because it has more resonance. And then this is just the only valid resonance structure that it shows. Does that make sense? Okay. So the next one. What is the order of the acid strength from strongest acid to weakest acid? So this is pretty much just an induction question. Hi, are you here for Orgo 2? Perfect. You guys remember induction, right? So we can draw our little arrows this way. What makes something having more of an inductive effect? Yes, being more electronegative, right? So what's more electronegative, fluorine or chlorine? Fluorine, right? And then is it better to have this negative charge closer to the acid, closer to the oxygen that's getting deprotonated, or further away? Closer, right? We want that induction to be closer. The further away it goes, the less the inductive effect is there. So to answer this question, we're going to look at these two, right? Because these two have their electronegative heteroatoms closer to where you're going to deprotonate your hydrogen. And this one is fluorine and this one is chlorine, so that means 3 is going to be the strongest, right? So we can eliminate D and A. And then from there, C is the next strongest because it also has those inductive atoms right next to the oxygen that you're deprotonating, but it's just a little bit less electronegative, so that's going to be the next one, so we can eliminate B. So we already have the answer. And then from there, the fluorine is just a little, even though it's one space away, still is going to have an inductive effect, so it's going to be a little bit of a stronger acid than just your regular carboxylic acid. So that's why the answer for that one is C. No, they're both the same distance away. They drew it kind of weird. This one has the Cl2, I'm sorry, the Cl3 and then the C, right? And this one has the F3 and then the C. So, two and four. Yeah, the closeness matters more than the electronegativity. Yep, so yeah, that's a great question. So yeah, the Cl one is going to be a little bit more acidic because it's right there, versus even though fluorine's a little bit more electronegative, it's a whole carbon away, and that is going to decrease it more. No problem. Any other questions? Okay, so we have another acidity question. I like this question. The reason I picked this question is because it's an acid question, which is Orgo 1, but it's using Orgo 2 topics, so I figured it would be a good one. So it says, identify the weakest acid. So when you're an acid, you're going to deprotonate, right? So you're going to look something like this. Oh. You're going to look something like that, right? You'll have that negative charge. These are all benzene rings, and we notice that we have some kind of groups on them, right? Activators and deactivators. Do we remember that from this chapter or this year? So your activators, are they donating electrons or are they withdrawing electrons? Activators donate electrons. So your activators are donating electrons, and you already have a negative charge, right, when you're an acid. So are you going to want something that's donating electrons to your benzene ring? No, right? You don't want to have more electrons if you're going to have a negative charge. So the weakest acid is actually the one with the strongest activator. So this NO2, that's a moderate deactivator, right? So that's actually going to make it a stronger acid. This Cl, that's a weak deactivator. So again, it'll make it a little bit stronger of an acid. And then right over here is actually the moderate. It's either moderate or strong, I can't remember. But it's definitely an activator. So that one's going to be the weakest acid, because you have something on the benzene ring that's donating electrons, and the point of an acid is going to have that negative charge after it gets rid of its hydrogen, so it doesn't want that. Does that make sense to everybody? Any questions? Why not A? Because A has nothing, right? So A is neither being helped by a deactivator nor hindered by an activator, right? So this is going to be a little bit of a stronger acid than this one, because this one doesn't have any extra electrons inside the ring, right? And we don't want those. Those actually hurt us as an acid. So it'll actually be a little bit stronger than C, because C is going to be hindered by the fact that it has extra electrons in the ring. Does that make sense? Oh, to rank it, the moderate deactivator would be the strongest, right? Because that's pulling electrons away. That's helping to stabilize the negative charge. Then I believe it would be the weak deactivator, and then it would be the regular, and then it would be the activator. Does that make sense? Yeah. Okay, good. Good questions. Okay. So which protons in this compound would be most acidic? So this question, I initially saw right away, well, I like my protons that are next to my benzene ring, right? Because if I lose those, my negative charge can go all the way through my benzene ring. But this proton on letter A is also on an oxygen. And you would definitely rather have a negative charge on an oxygen versus a carbon, right? So that's going to go, and it's just going to make A the strongest acid. Having all of that resonance in the benzene ring contributes to acidity way more than being next to a carbonyl would. So the OH on the phenol is way more acidic than any of the other hydrogens, because you have the stability from your negative charge being on the O, and you also have the stability from all the resonance inside the benzene ring. Does that make sense? Any questions? Yeah, so when you're talking about acidity, that means you're donating a proton, right? AKA deprotonation. So if it helps you think about it, or draw like the part of question without a proton. Think of that as negative. How can I stabilize my negative charge? Resonance, I can stabilize it by withdrawing electrons, right? Adding electrons is bad. Okay, cool. So we're moving on to stereoisomerism. This is again some Orgo 1 stuff, so we'll see. Okay, so which molecule has the R configuration? So is R clockwise or counterclockwise? Clockwise, right? It's the right way, is how I remember it. So we're looking for something that is clockwise. So we're just going to start at our chiral